Now that we learned how to search for things in arrays, and now that we had a look at a couple of search algorithms, it's time for the next logical thing, which also often helps with searching, by the way, and that would be sorting. In this module, we'll explore sorting algorithms. So, algorithms that allow us to sort arrays of data. Now, first of all, we'll have a look at what sorting is all about, what I mean by that term. And then, of course, we'll have a look at various sorting algorithms with different time complexities. We'll derive those algorithms together, and we will, of course, also explore why certain algorithms have the time complexities they do have. So what is sorting? What are the algorithms in this module all about? Well, this should be fairly straightforward. Sorting, of course, is about having an array full of data which is unsorted, so which is not in the order you want it to be. And then with the right sorting algorithm, you can efficiently derive a new array that is sorted, so where the items are put into order. And of course, you can sort them in an ascending or descending way, but that's totally up to you. The algorithms will always work in the same way though. Now in this module, we'll have a look at various algorithms that help us achieve that goal of sorting items. And being able to sort lists, so to sort arrays, is of course super important. Because often in programming, you have other tasks like finding elements or splitting lists or doing anything else that need sorted data. So let's explore various sorting algorithms then. Now we'll start with the bubble sort algorithm, which is, I would say, the easiest and the simplest sorting algorithm you can come up with. Now here we have an unsorted list, and we would sort this in ascending or descending order with the bubble sort algorithm by comparing two items at a time and then by, well, sorting these two items. And we would go through the entire array multiple times, every time comparing two items at a time for the entire array until all pairs were compared and sorted. So let's now have a look at that in theory. We would start with the first two items in the array, so with item 1, the item at index 0, and item 2, the item at index 1, and we would compare those items, and depending on whether we want to sort in ascending or descending order, we would check if item 1, the 3 in this case, is greater or smaller than item 2, the 10 in this case. Now let's say we want to sort in ascending order, so we would check if the first item, 3, is bigger than the second item. If that would be the case, we would need to swap those two items to, well, put them in ascending order. Here, of course, that condition would not be met because these two items already are sorted correctly. They are in ascending order, so we would move on and compare the first item to the third item, minus 3 in this case. Now we apply the same check. Is that first item greater than that third item? If yes, we need to swap them because these two items then certainly are in the wrong order. And for that, it does not matter that there's an item between them, the 10, which might be even bigger than any of those two items. We'll take care about that in the next iteration. As I said, we're going to compare all pairs, and we're going to do that multiple times. So here we're looking at 3 and minus 3. And we would, of course, find out that minus 3 is smaller than 3, so we need to swap those two items, and that is what we would do. We would swap those two items in our array. And now important, we keep comparing the first item to the next item. So we're not going to compare 3 to 48 now, but instead minus 3 to 48. So we stick to the first item, and it doesn't matter that the first item changed. We focus on the first item by index, not what was previously the first item. So we compare our new first item to the next item in line, which is 48. We check if our first item is greater than that, and if we therefore need to make a swap. But that's of course not the case here, so we keep it the way it is. We move on to the next item, no swap required here either. So we move on to the next item, no swap required, and also not for the last item. So now we're done comparing the first item to all other following items for the first time. Now we move on to the second item in the array, and we again compared it to all items after it. And that's important only to the items after it, because we know that the items in front of it have to be smaller already. So we compare 10 to 3, and we make that check if 10 is greater than 3, which of course is the case. So we need to swap those two values. Now again, we stick to the second item. The fact that it's swapped does not matter. So we're going to compare this new second item to the next item in line, the 48. And we check if 3 is greater than 48, in which case we would need to swap those values. Now, no swap is required here, so we move on and compare it to 5, no swap required. Compare it to 33, no swap required. Compare it to 99, no swap required. And we move on to the next item in line. Compare that to 48, no swap required. Compare that to 5, and a swap is required. So we do that, and we compare that new third value, the 5, to the next item in line. No swap required, no swap required for 99 either. So we move on to the next item. We compare that to 10 in this case, and 10 of course is smaller, so we need to swap those two values. Now we compare 10 to 33, no swap required, and no swap required either for 99. We move on to the next pair. Here we do need to swap them, of course. And then we compare that, and we move on to the last pair, compare those two. No swap required, we got our final list. That's how the bubble sort algorithm works. We go through the list multiple times, and we every time compare one item to all the other following items in the list. Now let's see how we could write this algorithm in code. So let's write our bubble sort algorithm, and for that I'm back here in an empty project, empty app.js file, which is getting imported in the index.html file. We're going to write the algorithm here. So let's add a function, and I'll name that function sort, because that's what we're going to do. You could of course also name it bubble sort to make it super clear which algorithm you're going to use, but I'll just name it sort because ultimately that's what we're doing. And as an outsider, if we would be another developer calling that function, we wouldn't really care about the implementation of the function. So just sort. Now, sort should be callable with an array which we feed in as data. An array that can be stored in a variable which we feed in, or simply here on the fly created. And that can be an array of various values which, well, are unsorted, as you can see. I just entered some random data here, and as you can see, it's not sorted, neither in an ascending nor in a descending way. Now I want to be able to call this sort function like this and get back a sorted array, which I then can console log or do whatever I want to do with it. For example, search for an item in case we have a search algorithm that needs a sorted array. We saw such an algorithm too in the last course module. There we had the binary search algorithm, and as you learned there, the binary search algorithm needs a sorted list. So this would be an example of how you could get a sorted array. Well, almost, of course. Right now, sort is pretty empty. Now, sort would get the array which we want to sort as an input, and it should return, let's say, a brand new array, which is our sorted array. For that, in the sort function, we can add a new constant, result array, for example, and there I simply copy the array I get as a value, for example, with array slice like this, or by creating a new array and using the spread operator. And I'm doing that so that if I change the array, the result array now, I don't change the original array. Since arrays are objects and they are for reference values, we would change the original array if we start working on the array here in the sort function, and I don't want to do this. This array, which I get as an argument, that should not be changed. Instead, a new array that is sorted should be generated. Hence, I copied the array I get as a parameter, and we can now work on that result array without changing the input array. Now for the actual algorithm. How does this bubble sort algorithm work? We actually will have two nested for loops. we'll have one outer for loop, which I'll simply name outer. My iteration variable is named outer, which starts at 0, and I proceed as long as outer is smaller than result array dot length, and I add 1 to outer after every iteration. Now I'm naming this iterator variable outer here so that it's easy to identify inside of the loop later. Because, as I just said, we will also have another loop in there, a nested for loop, which I'll of course name inner. And that inner variable will basically be my outer variable plus 1. So for the first loop iteration of the outer loop, that will be 1, because outer is 0, outer plus 1 is 1. And we will continue in here as long as inner is smaller than result array.length. So that's the same condition as in the outer loop here. And just as in the outer loop, I'll increment inner by 1 here. So we got 2 nested loops here. Why do we need nested loops? Well, keep in mind what you saw on the slide. There, we in the end compare 2 values, and we go through 2 values, therefore we need 2 loops. We change the first value, and we change the value for every first value we're comparing it to. So here you could say 3 is our outer value, minus 3 is our inner value. And then we swap them, so now we got a new outer value, but still, we got that outer position, that outer index, which still is 0, and we're comparing that value in that index to all following values, and that's our nested loop. So now we're comparing it to 48, and to 5, and to 33 thereafter, and so on. So that's what we're doing here. And this item on the right, which is moving from 33 to 99 now, for example, that's our inner loop. Eventually, that inner loop finishes once we compared the outer element, the first element here, with all other following elements. And then we go to that outer loop and increment outer to 1, for example, to have a look at the element at index 1. And now again, run the nested loop for all other elements following that, which is why we have outer plus 1 as a value for inner. We look at the element at the next index. So now again, we have a swap here, but that doesn't impact our loops. We continue running through those nested loops, and now we go through all those elements again in the inner loop until we reach the last element here, and then the inner loop is done again, and the outer loop increments the value to 2. So now we have a look at the element at index 2 in the outer loop. So that's why we have nested loops, because we change 2 elements and we compare all elements to all other elements, hence the nested loops. Now in the outer loop, before we enter the inner loop, we therefore define our outer element. And for that we have a look at the copied array and get the element at index outer. So for the first iteration 0, for the second iteration 1, so the second element, and so on. Now inside of the inner loop, we now have the inner element therefore, and that is result array for the, you guessed it, inner element. So for the first loop iteration of the outer and the inner loops, for the first iteration of each loop, that would be the second item in the array, because inner initially is outer, which is 0, plus 1. So that's 1 overall, so the index 1 passed to result array, and that's the second element. So for the first iterations, we have the first and the second elements here. And now we simply compare them. We check if the outer element, which is the first one, if that's greater than the inner element. And here I'm writing the algorithm to sort in ascending order. If you want descending order, you would basically revert this. So here I'm checking for outer L greater than inner L. If that's the case, if the first element in the array is bigger than the second element, we need to swap them, right? Because then we have a bigger element in front of a smaller one, and for ascending sorting, that's the wrong order. So we would go to the result array, access the element at position outer, so the first element for the first iterations, and set the element that's stored in that position in the array equal to the inner element. And we would also go to result array, and for the element at index inner, we would set the outer element. That simply swaps these two elements. So if we have this on an array that looks like, let's say, this, the result would be this. Because we take the index of the outer element, which is 0 for the first iterations, so the first element, and replace the element there with inner L. So the old outer L is replaced with inner L, but we saved outer L into a separate variable before we did that, so we can still use that outer element to, in turn, replace the old inner element with it. So the old second element with the old first element, and the other way around. That's what we're doing here. And in case you can't wrap your head around this, simply dump in a console log thereafter to see what you're getting. So that's what we do here. Now, of course, if we swap elements, we now also need to update our references. So outer L is now result array outer, and inner L is now result array inner. Now we're doing this here because I changed the elements in the outer and inner position. We swapped them. So now that we used these elements stored in our variables to swap values, we got the right values in the array, and we can now, on the other hand, also replace the values stored in our helper variables here. We need to do that so that for the next loop iteration, we have the right values set up, especially for outer L, instead of the inner loop here, that we're operating on the new outer L, which is our swapped value. Again, you can always console log these things if this is a bit too hard to wrap your head around. With that, however, we're already done. Now we go outside of all loops, so here right before the function ends, and we simply return our result array, and that should be the sorted array. Now let's log it before we analyze it then. So I'll save that and reload. And what I get is this array, which looks quite sorted to me. Now let's check if descending sorting also works by simply switching that condition here from greater than to smaller than. And that looks like a descending order to me. So that works. Now in order to understand what's going on, let me add a couple of console log statements. Here I add an outer loop console log statement so that we can see that we're in the outer loop. And I'll log what's currently in outer L at this point of time. Then I'll copy that and go into the inner loop to then output my inner loop value. And I will also output what's in outer L at this point of time and what's in inner L. So that's what's stored in these two variables inside of the inner loop. And now inside of the if statement here, I'll add a console log statement inside if, and console log my result array the way it looks at the end of this if statement. And here I'll add another console log statement, end of inner loop, and also output my result array at this point of time. Keep in mind that we don't always make it into the if statement, so that's why I add these extra logs here. With all these logs added, let's reload. And of course, we got a bunch of logs here, as you can see, because this all runs a bunch of times. Let's see if we can make sense of that. We start in the outer loop, and we got a value of 5 here, which is coming from line 7, and this is simply what's inside of outer L. We get 5 here as a first value because that is the first value in the array I'm passing to the sorting algorithm. Now actually, to make this a bit easier to digest, I will temporarily comment this out and remove most values so that we just have 3 values here, so that we got less output here in the log. This should be easier to go through. Nonetheless, we have 5 as a first output. Now we see inner loop, and we get our current values for outer L and inner L, 5 and 10. Now just keep in mind, that's coming from these lines here. We got 5 and 10 because these are the first 2 values in the array we want to sort, and I mentioned that we would select these first 2 values with the logic we wrote. Now we're at the end of the inner loop, and that tells us one important thing. we don't see any log from the if statement, so we didn't make it into the if statement for that first loop iteration. And correctly so, because these two items, 5 and 10, already were ordered correctly. We already had them in an ascending order, so there was no work to do, no swapping to be done, hence we didn't make it into the if statement, hence we're now at the end of the inner loop. So now we start the inner loop again. That's what we see here, lines 11, 12, and 13. Here we are. And we get the new values for outer L and inner L. Now, previously that was 5 and 10, now it's 5 and minus 3. And that's important. The outer L here still is 5. So I'm still comparing that first value of the array to the next element in line. We have outer L 5, and we're now comparing it to minus 3. Now, minus 3 is the next element in line in our input array. So we had the comparison of 5 and 10 and had no changes there. So now I stick to 5 and compare it to the next element. Again, comparing pairs of values, just in this case, not pairs of side-by-side values, but simply first value with all values, then second value with all other following values, and so on. So 5 with minus 3 is what we're comparing now. And now we make it into the if statement, as we can tell by the inside if output here. And at the end of the if statement, you see that we swapped minus 3 and 5. Originally, the array was 5, 10, minus 3. Now it's minus 3, 10, 5. And we swapped that because that's the logic we wrote in here. The outer L, which is, as you can tell, 5, is greater than the inner L, which is minus 3. And in that case, we make it into the if statement because then the order is wrong. So now we swapped that, and we ended up with this new array. And we're done with the inner loop. This is the end result of that inner loop, and now we start a new outer loop. So now we're done with all inner loops because for the first value, the 5, we went through all other values that followed it. Now, if we had another iteration in the inner loop, because we had another fourth element in the input array, the next outer element we would use for the comparison would be minus 3, by the way, no longer 5, because our first element changed. That's why we're updating outer L here in the if statement as well. You can easily see this if you add a fourth element here, let's say a 1. If I add a 1 here and I reload, we have everything like before. You see we're inside the if statement, we got minus 3 and 5 swap. We're done with this iteration of the inner loop, but we would now start a new iteration of the inner loop because we have the fourth element, another element to compare to the first element, but the first element, the outer L, now changed. It's now minus 3 because of our swap, and we compare that to the next element in line, to the 1 here. So that's how this would work if we had 4 elements, but for simplicity's sake, to make this easier to go through, I'll remove it again and reload, and go back to the point where we were, the end of the inner loop. Now we start a new outer loop as soon as we exhausted our array and we compared the first element to all other following elements. Now we move on to the second element in our current result array, which is 10. That's the new element we're going to compare to all other elements after it. We're not going to compare it to minus 3 because we know what's in front of it has to be smaller, but we're going to compare it to all other following elements. So we start a new inner loop. Outer L is 10, inner L is 5 because that's the first following element. We make it into the if statement because, of course, because of this condition here, our outer L, 10, is greater than 5. So we swap these two. We're done with the inner loop, that's our end result, and we start a new outer loop where we now have a look at 10. Now we want to compare 10 to all our following elements, but since we have no following elements, we're simply done, and we have our final result array which was returned. That's how the bubble sort works. We're simply comparing pairs of values, and we go through the array multiple times until we had all necessary comparisons. Now what about the time complexity of that? Let's analyze the time complexity of the bubble sort algorithm in the best, average, and worst case. Now, the best case is that the items are already sorted. If we have that case, we actually have a time complexity of O of n. So we have linear time complexity. Now, why is that? Well, if we have sorted items, we only have to go through the loops once. We can check this. If I pass in a sorted array 1, 2, 3, and I save that and I reload, you see with the outer loop starting, the inner loop starting, inner loop done, new inner loop starting, and so on. So we're starting all those loops, but if we have a look at the actual work that's being done in every loop, that's basically nothing. Going through that inner loop is pretty redundant, and we're not doing any actual work in there. We're storing a value in our helper variable, but we never make it into this if check because we already have sorted values, and we could remove all console log statements therefore, and hence there's nothing left to do here. In the end, we're doing nothing in that loop, so we can't pretty much count this as not a loop iteration, if you want to call it like this. So we basically have no work to do. That's why we can say that we have linear time complexity here. We need to go through the entire array and do all these comparisons, but we never have any actual work to do. Now, what would be our worst case? The worst case is that the items are basically sorted in the wrong order. And in that case, we have a time complexity of O(n) squared, so quadratic time. So in this case, this would be that we have 3, 2, 1. If we have this array, we need to go through all loops and we need to do all the work in every loop. For every loop here, for every inner loop, this if check returns true because 3 compared to 2 is true. We need to swap them. 2 compared to 1 is then true thereafter. And 3 compared to 2, which will be our swapped array values, will also be true. So we always make it into the if check. We always do all the work here. Both loops have full effect, you could say. And that's a simple rule of thumb. If you have nested loops, you're dealing with quadratic time. Unless you do stuff like halving your input or anything like that. But if you're not reducing your input, if you're not splitting your array or anything like that, you have quadratic time. It's a simple rule of thumb. 1 loop, linear time. 2 loops, quadratic time. 3 nested loops, cubic time, and so on. That's basically how you can think of that, unless you're doing anything special in there, like splitting the array into smaller chunks or anything like that. So that's why we have quadratic time here. And as so often, that's also our average case here with the random order, which tends to be quadratic time because we'll typically have at least a couple of items which we need to swap. So quadratic time is basically the time complexity we have for the bubble sort algorithm. That's not that great. It's not as bad as exponential time complexity, but it's certainly not good. It means that for very long lists, we got a lot of work to do because of all these value comparisons, because of all these pairs which we're comparing multiple times. Maybe we can do better. We had a look at the bubble sort algorithm, a fairly simple and easy to implement algorithm that tends to give us O(n) squared, so quadratic time complexity. Maybe we can do better, and we can. Let's now have a look at another sorting algorithm which we can apply, and that would be the quicksort algorithm. Now, how does the quicksort algorithm work? It's also a fairly simple algorithm, I can say that, and it will use recursion to sort elements. The idea on the quicksort algorithm is that you use pivot elements to split the array into smaller chunks. You simply choose one element in the array and then you find out which elements in the array are bigger, smaller, and equal than the pivot element, and you put those elements into 3 different chunks, into 3 different new arrays, and then you repeat the process for those arrays. So you pick a pivot element, often that's simply the first element in the array, so you don't take the middle or anything like that, but simply the first element, because the array is unsorted anyways. And then you create 3 new arrays, a smaller chunk or a smaller elements array, equal elements array, and a larger elements array. And you then put the pivot element into that center chunk, into that equal elements chunk, and any other elements of the same value would go into that same chunk. Smaller elements go into that smaller chunk, into that smaller elements array, and larger elements go into that larger elements array. So now we have 3 arrays with elements, and now we simply repeat that process. We create 3 new arrays, and again we choose a new pivot element, and we do that in every array, by the way, not just in the large elements array, but we would do this in every array because we could have more items than just one item in every array. So we would repeat that process, pick a new pivot element, and if we here on this slide focus on the elements which were greater than our old pivot element, we would split this array into 3 new arrays in a recursive step and put our new pivot element into a new equal elements array in that recursive function, have a smaller chunk array and have a larger chunk array. That's how it would work. Now at the end of the algorithm, we would therefore kind of end up with a bunch of elements separated in separate arrays, and we would simply concatenate all these arrays together, and they would be sorted correctly because of that splitting we make in every recursive step. Now that's the logic behind the quicksort algorithm. Now let's implement it in code. For that, I'm back in an empty app.js file, and in there we'll add a new sort function, and that sort function will again take an array as an input, so that we can call it with any input array of our choice, -3, 10, 1, 100, -10, 22, 15, something like that. Now this should then again give me a sorted array, and I want to console log that sorted array thereafter to see whether that worked. Currently it's of course not really sorted, as you can tell, -10 should be the first value after all, and so on. So previously we implemented this with a bubble sort, now we're going to use the quicksort algorithm. Now how do we do that? Inside of that sort function, I again first of all copy that array, because I'm going to change it and I don't want to change the original array. So I'll name this copied array here, and again simply use the spread operator to copy the array we get as a parameter into a new array. Now we can change that copied array inside of the function without changing the input array. How does this algorithm now work? What are we doing with that? Well, first of all, we can check the copied array length here. And we do this to have an exit condition, a base case, since we're going to write a recursive function. So I want to check if the length is smaller or equal than 1. If that's the case, I want to return the copied array. I don't want to call myself again. I don't want to have another recursive step. We don't have any recursive step right now, but we're going to add one. And since, as you saw on the slides, since we're going to split that array into a bunch of individual arrays, which in the end are always arrays with just one element, we check if an array is one element long or shorter, in which case we know we're done. We don't need to split this array anymore, so we just return that array with that one element here. Now, what are we doing outside of this base case though? Now here we need to do that splitting. So I'm going to construct 2 new arrays here, and I'll name it the smaller array or smaller elements array to make it really clear what will go into that array, and the bigger elements array to make it clear what will go into this array. Now I'll also add a center elements array, or I could also name it equal elements array, which will be our third array in the middle. And this array, the center elements array, will contain our pivot element. So I'll also get that pivot element here, and that pivot element simply here could be the first item of the array we got. So the first item of the input array, and for that I'll use copied array shift. Shift is a method which is available on arrays in JavaScript, and it shifts the array to the left. So it moves all items to the left and therefore drops the first item, which however is not lost but instead returned by shift. So this stores the first item of copied array in pivot element and changes copied array to only contain the remaining items. And 10 would then be the new first item. So I change copied array, and that's why I do copy array in the first place, and store the first element of copied array in pivot element. And pivot element now is added to that center elements array. That's also what I showed on the slide. The pivot element goes into that middle array. And now all items that are equal to pivot element in copied array would go into the center elements array as well. So that's something we will need to check, but we need to check that for all items in the remaining copied array. So we have to go through that array. And I will use a while loop here because I'm going to manipulate that copied array throughout that while loop. So here I have my while loop, and I want to continue with this loop as long as copied array length is truthy, which basically will be the case as long as length doesn't reach 0. So as long as the array is not empty, we'll continue in the while loop. Now we will gradually make that array empty inside of the while loop so that eventually the loop will stop. Now inside of that while loop, we have a look at every element, the current element, by simply repeating that copied array shift process. We used it once to get the pivot element. Now inside of the while loop, we're doing it to get access to the next element, so to the new first element of that copied array. And that manipulates copied array, so the length shrinks by 1 for the next iteration. So we retrieve the first element of the copied array, and we remove it from that copied array thereafter, and shorten that copied array. And now we need to check this current element. We want to find out if current element is equal to the pivot element. If that's the case, the current element, so the element we're currently looking at, should go into the center elements array. So here we have the center elements array, and we push the current element into it if this element is equal to the pivot element. So in case we had another -3 in there, that would go into that center elements array. And let's add it here to prove that it works. Now we also, of course, might have the case that the current element is smaller than the pivot element. So I'll add an else if check and check if current element is smaller than the pivot element. Since our pivot element for the first iteration is -3, that would, for example, be the case for -10. Once we have this as a current element, it will be smaller than our pivot element. So here we see that it is smaller, so we add it to the smaller elements array. We push the current element to the smaller elements array. And else we know it's greater, so we use that bigger elements array and push current element into that array. So now every element of that array will be put into one of those 3 arrays, which therefore will have different lengths. Since we change copied array with every iteration, because shift does remove that first item, it shrinks, and eventually copied array will be empty, at which point it has a length of 0, which will then exit this while loop. Now we're done with the while loop. We got our 3 new arrays, the center, the smaller, and the larger, or the bigger elements array. And now the question is what? Now we did this once, but now we need to repeat this for every new array we generated. Except for the center array, because that only contains elements which are equal anyways, so we won't need to sort those into different arrays. So we need to repeat it twice for the smaller and bigger elements array. Hence, we will in the end call this sort function again recursively, 2 times for the smaller and bigger elements array. So we got our smaller elements sorted array, a very long name, but I want to be clear what's in there, by simply calling sort again and passing the smaller elements array to it. And we repeat that for the bigger elements sorted array, where we pass in the bigger elements array. So here we call ourselves recursively with the sort function, and with that we'll get 2 new arrays in the end. Now these are recursive calls which go through that whole process again, but ultimately, as always in recursion, all those nested function calls are going to finish, are going to return their overall results, and we're going to get those overall results back in this main function call in the end. So in the end, we'll have sorted arrays for smaller and bigger elements. We have the center elements array, which contains only equal values anyways. So now we can return the smaller elements sorted array, call concat on it, which is a default array method in JavaScript, and concatenate the center elements array as well as the bigger elements sorted array, so that we build one new long array by combining these smaller center and bigger elements arrays. And that's the overall result we return. Now let's see whether that works before we put in some logs and also judge the time complexity. Let's save that and reload. And you see what I get back is this array, which looks quite sorted to me. Sorted in an ascending order. If you want to sort in descending order, you simply need to switch your if logic here. Now that looks pretty good. Now let's understand how it works. And to understand this, I'll shorten it a little bit. I'll add, let's say, -3 here and also -10. But that's it. I'll copy that, comment this one out, and now shorten this one to only have, let's say these 4 elements. -15 works too. So these 4 elements. And now let's dump in a couple of console logs. Let's add one here at the beginning, function starting. And let's simply console log the array we're getting. I could also log the copied array, but that will be exactly the same here. Well, if we make it into this check, I want to know. So I will output only one item returning here so that we see when that is the case. And I can console log my one item array in that case. So I'll console log the copied array in this case. And of course, we also want to know what's going on down there. So after that while loop, I will console log after while, and then console log the smaller elements sorted array, and not the sorted array, sorry, but the smaller elements array, and also the center elements array and the bigger elements array. And with that, let's save it and let's reload. And of course, we get quite some outputs here, but not too bad. So let's go through that to understand how this algorithm works. We're starting the function, unsurprisingly, and we get an array with 4 elements, which is, of course, that input array we got here. Now, after the while loop, you see that our smaller elements array, which is the first one we're logging here, right? That's this log from line 29, has only one element, -15, which makes sense. Our first pivot element will be -3, and there is only one smaller item here, which is -15. We have one other element in the center array because -3 occurs again, and the bigger elements array only contains only one element, 10, which is the only one bigger element. Then the function starts again for our 15 array, but that's only one item, so we return. We then also start again for 10, but we only have one item, so we return. And so we're done. Now that wasn't too interesting, so let's add one more element here. Let's say we also have 100 in there, so another bigger element. If I now reload, you see we got this array. Now after the while loop, we got still only one element in the smaller array, 2 elements in the equal or center array, but also 2 elements in the bigger elements array, 10 and 100, because they both are bigger than -3, which is our first pivot element. The function starts again for -15, so for the smaller array. There's only one item, so we return. The function starts again for 10 and 100. That's our bigger elements array. And after the while loop, you see the smaller elements array is empty, which makes a lot of sense because 10 was the pivot element that was picked, which is why it's in the center elements array. And there are no smaller elements in there, so that array is empty. The bigger elements array has one element in it, 100 though, which also makes sense. So we call the function again for the empty array. Well, that's only one item, or no item to be precise, so we return that empty array, which was that smaller elements array. And we start the function again with the 100 array, so the bigger elements array. It's only one item, so we return that, and then we got that overall sorted array here. And that's the quick sort algorithm, really not too complex. Now, does it perform better than the bubble sort though? Is it better than that? Let's have a look at the time complexities of the quicksort algorithm in our different cases. Now, the best case is actually that the items are sorted randomly, so that they're not sorted, that they're not in the right or wrong order. If that's the case, then this algorithm is able to perform best. And I can tell you that in that case, it will have a time complexity of big O n times logarithm of n. Now, we'll derive that ourselves in just a second. I can already tell you that this will be the case. In the worst case, on the other hand, items are sorted, and that is actually bad for this algorithm because since we always take the first element as a pivot element, we will always end up with a case where one array, the smaller elements array, for example, is empty, and the bigger elements array has all other elements because they're already sorted. And in such a case, we will have a disadvantage in this algorithm, and we will end up with quadratic time complexity. Now, why will that be the case? Well, we have this logarithmic time complexity, times n, but still with a logarithmic nature, because we generally split our problem into smaller problems, right? We split our array into sub-arrays. And you learned in this course already, if you're doing that, if you're splitting your problem into smaller problems with every iteration, you tend to work with logarithmic time complexity. Now, if you're dealing with an array that's already sorted, so something like, let's say, 1, 2, 3, then the problem is that since we're always taking the first element as a pivot element, we always have one empty array, the smaller elements array, if we're sorting in an ascending order, and we have one large array, the bigger elements array. And therefore, effectively, we don't split the problem into smaller problems because one array, the smaller elements array, is always empty. So we're not really splitting it. And therefore, we don't have the logarithmic advantage. We're not making the problem smaller. Instead, we effectively just go through the entire array multiple times with a loop inside of a nested function call. And that is simply quadratic time complexity. Because another rule of thumb, if you're calling yourselves inside of a function, so if you have a recursive function, you typically have linear time complexity. But if inside of that recursive function you then have a loop where you go through the entire array again, it's the same as having a nested loop in a loop. And that is quadratic time complexity. So that's why this is our worst case. Now, in the best case, we do split our array. And we do roughly do that in equal chunks. So we have a smaller elements array with some items, and we have a bigger elements array with some items. So in that case, we are roughly splitting the problem in half with every iteration, and that's why we're getting closer to that logarithmic time complexity. So that's the difference between best and worst case here. Now, the good thing is, on average, of course, we don't really have a sorted array. Because if we know that we always have sorted arrays, we wouldn't need a sorting algorithm. So on the average case, we can rely on the problem, the array being split into roughly equal sub-arrays. And therefore, in the average case where we don't have sorted items, we also have that best case time complexity, which is better than quadratic time complexity. N times logarithm of n is better than quadratic time because it grows slower. It's simply mathematically smaller. Now, how do we derive this big O notation of n times logarithm of n, though? For that, we use that good old master theorem again. There, we had two steps, basically. We calculate the runtime of the recursion with that first formula, and then we also have a look at the runtime outside of the recursive step. We compare these two runtimes, and based on where more work is being done, we derive one of these final formulas. So let's do that step by step for our problem now. Let's derive the recursive step runtime here. And that's done with that first formula on the slide, which was O(n) at the power of log b of a. Let's write it like this maybe. So, what would this look like here? Remember that A equals the number of subproblems, so how many recursive calls are we making? And B equals the relative subproblem size, so which kind of split are we making? Now here, A, the number of splits, is 2 because we're calling ourselves twice. And B, the kind of split, is roughly also 2. Now, of course, we don't know this in detail. It depends on the input array. But on a random input array, which is not sorted, we should generally have equal sizes for the smaller and bigger elements arrays. So A and B should both be 2. So we have O(n) at the power of log 2 of 2. Now, what is log 2 of 2? If we quickly plug this into a logarithm calculator here, we see logarithm at the base of 2 for 2 is 1. So that's 1 as a result. Hence, this is in the end O of n at the power of 1. And that, of course, is O of n. Okay, so our recursive step runtime is O of n. We can keep that in mind. Now, let's simply have a look at the runtime outside of the recursion, so the rest of the code. And there, the primary thing we have here is a while loop. Now, it's a simple while loop, no nested loop, and we go through the entire array here, because we're shifting one element per iteration, and we do that until the array is empty. So we go through the entire array here, and as you learned, if you have a loop where you go through all elements of an array or through all numbers up to a number, you have linear time complexity. So this is also O of n, linear time complexity. So the recursive step has linear time complexity, and the runtime outside of the recursion also is linear time complexity. And therefore, if we're back on this slide and we have a look at these 3 cases, we're in the middle case here. We have the same work being done inside and outside of the recursion, and therefore the overall algorithm runtime is derived with this formula here. So that's our overall algorithm runtime here. Algorithm runtime is therefore O of n at the power of log base b of a, and then times log n. And that's not at the power of, but after this term here. So that's our overall algorithm runtime as defined by the master theorem. Now we learned that this part here, which is the recursive step runtime, is O of n. And therefore, we have O of n times log n. And this is our final algorithm runtime. Now that's exactly what I showed you on this slide, and that's how you can derive it on your own with the tools you already learned. The quicksort algorithm certainly was an improvement over the bubble sort algorithm. After all, in the best and most importantly, in the average case, we are able to achieve a time complexity of n times logarithm of n, which is better than O(n) squared. Yet we have that worst case with that quadratic time complexity. Now maybe we can do better than that. Well, indeed we will be able to do better than that, and the reason for that is this pivot element which we use here in the quicksort algorithm. We always chose the first element, and in the worst case, where we have a sorted array, that is a problem, because then we always have one large array and one empty array. I talked about this in the last lectures. That means that we don't really split the problem into smaller chunks, and hence we don't get that better time complexity. That leads us to the merge sort algorithm, an algorithm which is also all about sorting a list, sorting an array, but it will give us a better time complexity. I can already spoil that to you. Now, how does the merge sort algorithm do that? With the merge sort algorithm, we split the array multiple times and always in the middle until we have only 2 element arrays left. So we split this array into multiple 2 element arrays, and we'll do that recursively, always by splitting in the middle. And then we sort those arrays and we merge them back together. So here's how that will look like. We got this array and we split it once in the middle, and if we have no perfect middle like here, well then close to the middle. So that in this case we have one 3 and one 4 element array. Now that's not the 2-element array I'm looking for, so we split this again. Recursively, we call that splitting or that sorting function again. Hence, we end up with these arrays here. We got a couple of arrays with only 2 elements and one array with 1 element. That won't be a problem though. So now we split everything the way we want, always in the middle, and we got these unsorted 2-element arrays. The next step is that we now focus on those 2-element arrays and we sort them. So in every 2-element array, we sort the items, and only inside of that 2-element array. Now, once we did that, we'll merge the arrays back together, hence the name, merge sort. We merge these arrays back together. Now, important, we merge them by keeping the order in mind. We don't just concatenate these 2-element arrays together. We didn't just concatenate the array with the 3 inside of it with the array with -3 and 10. Otherwise, we would have gotten an array that has the element 3, -3, 10. No, instead, when we combined these 2 arrays in the bottom left corner here, we did that with some extra logic that merged them into one array where the items are then ordered correctly inside of that array too. So if you want to look at it like this, we actually have 2 steps in that whole algorithm where we sort things. We order the things in the 2-element arrays, and then when we merge all these arrays together again, we again watch out for the order, and we again have some logic to order things correctly. And of course, we then do this one more time to merge this all into one big array. And it's based on this branch of subarrays which we built temporarily during our process. So that's the merge sort algorithm. We split things up, we sort them, and we also sort things when we then merge the arrays back together. Now let's have a look at that in action. Now for that, you know it, we're back in an empty app.js file, and I will write a sort function here. The sort function will receive an array, and I want to be able to call sort by passing in an array that, let's say, looks something like this here, maybe this, yeah, something like that. That's the array I want to be able to feed in. It's totally not sorted here, and it should be sorted. So that in the end, I have my sorted array here, and I then, just as before, can console log that sorted array. That's the idea. Now, how does the logic in the sort function look like then? Well, it all starts with us splitting up the array. That's something we do, as I said. We want to split the array into smaller chunks until we have only arrays with 2 or 1 elements. So here we'll get the middle, let's say, of every array, the middle index. And to get that middle, we take the array length and divide this by 2. Now, length is not always divisible by 2, or doesn't always give us an integer if we divide it. For example, if we have an array with 7 elements, this would be 3.5, and we need an integer value here. And therefore, we can again use math floor, something we also already saw earlier in the course. Now we got the index of the middle of this array, or one item to the left of the middle. Now with that, we have the middle. Now we can get the left array, if we want to call it like this, and the right array. The left array is our array, and we can use the slice method to get a slice, a part of that array, in a new array. Slice returns a new array based on this array, but only a part of that array. Now for the left part, we take 0 as the starting index and middle as the end index here. And then for the right array, we got slice starting at the middle, and if we don't specify an end index here, it goes all the way up to the end of that array here. So that's then our second array. We can temporarily log this here just to see whether it works. If I log my left array and I then log my right array here and I save that and load this, we see the left array has these 4 elements and the right array has these 4 elements. And That's basically this and this. And if I would introduce an extra element in the middle, let's say, or somewhere else, so that we don't have a even number of elements, we would see that one of the two arrays is longer. And that's totally fine. So we're splitting our arrays. Now the idea also was to sort the arrays, but only if there are only two elements in the split up arrays. And I'll actually do this before I split this, because I could maybe already be getting an array with only two elements. In that case, we don't need to do any other step. Or even if I don't get this, I want to run this logic before I split again. So I check if array length, so the length of the input array, is smaller than 2, if I have less than 2 items. So if I have only one item, or if I get an empty array, I return just that array. Because if it's empty or has only one item, there is nothing to sort. You can't sort just one item. If we have a length that is exactly equal to, not to 0, but to 2, then we know we have exactly 2 elements. And that's now the case where I want to sort those 2 elements. That's the first sorting step we have. So here I effectively want to return a result which is based on some condition, and I'll write a ternary expression here. I'll check if the first element of that array is bigger than the second element. And I know that there will only be 2 elements because I'm checking the length here. Now if the first item is bigger, and I want to sort in ascending order, then I know that I need to swap the order. Because the first item is currently bigger, in ascending order it should be smaller. So I'll return a brand new array by creating it here with the square brackets, and the first element in that brand new array will be the second element of the input array, and the second element in the brand new array, which I'll return, is the first element in the input array. So I return a brand new array with the swapped array elements. Otherwise, if the first element is not bigger than the second one, then I know they already are in the correct order, and I just return the input array. So these are these 2 cases. If neither of the 2 is true, I will go ahead and split my array into the left and right array. Now we need to call ourselves again to continue splitting and sorting these 2 element arrays. So I'll have my left sorted array here by calling sort again and passing the left array into it. And I'll repeat that, unsurprisingly, for the right sorted array, where I pass right array into it. So we have a recursive step here, and that's also why we need that base case first. We first need our exit condition, otherwise if we just call ourselves, we'll have an infinite loop. So we call sort again to split and eventually sort our array. Our 2 element arrays are then sorted. Now in the end, I don't just need to split and sort these 2 element arrays, but I also need to merge all arrays together. And for that, we need some merging logic, which I'll now add below. So here we call sort, which is a recursive call, of course. Now we need to merge our arrays. And for that, I will use a while loop here. Now, in that while loop, I, in the end, want to go through all the items in both arrays, which I want to merge together, and merge them into one brand new array, which, important, makes sure that items are added to it in the correct order. For that, I'll get my left array index here, which initially is 0, and my right array index here, which is 0, so that I have my whoops, that should be let. So that I have my 2 indexes and I can go through my arrays here step by step, element by element. And I need my new merged array here, which is an empty array initially. Now here in the while loop, I will check if left array index, so this brand new variable, if that is smaller than left sorted array length. I want to keep on running as long as my index is smaller than that length, which makes sense because I will change the index inside of the while loop, and I want to continue changing and incrementing it until I have gone through all the elements inside of there. Now I'm using a while loop because I don't just want to do that for one array. I could use a for loop in that case, but instead I will change both arrays at the same time in one loop. So I'll have a or condition here. I will keep on running as long as there are items left in the left array or in the right array. So we have the same logic there. Right R index, if that's smaller, whoops, and that should be left R index here, of course. So if the right R index is smaller than the right sorted array length. So same logic as for the left sorted array, but now with the right array. That's my logic. As long as there are items left in either of the two arrays, I'll continue in the while loop. Only if I've gone through all items in both arrays, I'm done. Now inside of the while loop, we now need an if check to find out what we want to do in there. We want to add elements to the merged array. We want to populate that merged array with new items. But of course, we want to populate it in the correct order. So what I'll do is I'll check if left sorted array for the left array index, which initially is 0. So if the first item in the left sorted array, in the first iteration at least, if that is greater than the right sorted array, and then they are the right R index. So for the very first iteration, where left and right R index are both 0, I check if the first item in my left sorted array is bigger than the first item in the right sorted array. If it is bigger, I know that the right sorted array item needs to be added to the merged array, because I want to have a ascending list, a list ordered in ascending order, so the smaller item should go first. So if we make it into this if check, I'll go to my merged array and push that right sorted array item for the right array index into it. So I'll push that item into my merged array. And then I'll change the right R index by incrementing it by 1. So we can move on to the next item in the right sorted array, because we already added the first item to our merged array. And of course, I only want to add every item once, so we increment that right array index. We don't increment the left array index because we haven't done anything with that first item in the left sorted array. It wasn't added to the merged array. We certainly don't want to lose it, so we must not change the left array index, not until we added this to the merged array. And we will add it in the else case, because if we have the opposite thing, that the first item is smaller than the second one, then I of course want to add my left item. So then I have the same logic. I'll go to my merged array and push the left sorted array for the left R index, and thereafter change the left R index by incrementing it. Same logic as before for the right index. Now that's how we will go through that. Now eventually, both indexes will reach the length of their arrays and will make it out of the while loop therefore. I also need to change that first if condition a little bit, because we need to add something there. We need to add an or condition here as well. We can always check the items in the two arrays, but what if we exhausted one array, but in the other array we still got an item left? To cope for that, we should check if the left R index is greater or equal than the left sorted array length. Keep in mind that the left array will always be the smaller one. If we split it, if we have an array with an unequal amount of items, the left array will always be the shorter one. So therefore, the left array will be the one that is exhausted first. That's why I check it here, because if the left array is exhausted, we know there has to be an item left in the right array. So we have to push the remaining right sorted array item into the merged array. And since this will be true if the left array is exhausted, we'll make it into this if block in that case and add the remaining right sorted array item to the merged array. We know that it has to be at the end of the merged array, so that pushing it there is correct, because every array itself was already sorted, thanks to this logic here, and then we merged all other items in the correct order. So we know with certainty that the remaining right sorted array item has to be the last item of this merged array. And with that, we are done. With that, we merged our items, and then we return that merged array here in the end. Now keep in mind, this is still part of the sort function, which also calls itself here, but that leads exactly to the behavior shown on the slides before. So if we now save that and we pass this array to sort, If I reload here, you see I get this array which looks quite sorted to me. And of course, you can add more items to play around with different arrays, and this should always work. Now, as I always like to do it, let's analyze what's happening here. And for that, I'll duplicate this and analyze a bit of a shorter array here. Let's say this one, or maybe one extra item. Let's say here we also have a 5. And let's say we want to analyze this array now. For that, I'll add a bunch of console log statements. One here at the beginning, function start. And here I'll console log my array, which I'm getting as an input. Now I'll also log here if we have an array of 2 items, exactly 2 items, and I'll then console log what I'll eventually return. So I'll console log this value here because that is what I'll return, so that we can see what this will return. I'll then also console log after recursive step, so that I console log the left sorted array and also the right sorted array. And of course, also after merging here. So after merge, I will console log the merged array. And with all those console log statements added, let's reload and let's analyze it. Our function starts and we get that input array, which of course is just that array we're working with here. Now the function starts again, and that should make sense because we call ourselves here, and the only other log we would have would be here in this array length 2 check. But of course, this array doesn't have a length of 2, so we don't make it in there. Hence, we skip all that code in the end, we slice up our array, and we call ourselves again, which is why the function starts again. This is now a nested function call, a recursive function call. We see we call ourselves again for 10, or for minus 10, I should say, and 33. So for this first left array. Then we see exactly 2 items, which indicates that we made it in this if statement, which makes sense because we got 2 items. And below that, I log what we're going to return, and that will be the input array. We don't need to change the order because it already is in ascending order. Now then we have another function start, and that's for that second array which we got here. We also got exactly 2 items, and here we return the swapped items, 5 and 100, because they were in the wrong order. Now we're after the recursive step. So the recursive calls finish their work. We have our 2 element arrays which are sorted, and now we need to merge them together. These are the 2 arrays we're working with. These are the 2 arrays that were returned, minus 10 and 33, and 5 and 100. So now we need to work with that. And after the merge, we see we have the correctly merged array. So that proves that this while loop seems to do its job correctly. And you can add more console logs in there, for example, in the if statement, if you're not sure how this works exactly. It does work, however, just as explained throughout this lecture and shown on the slides. We check all those items one by one and check if it goes into the merged array or if the other item goes into the merged array, until we have one merged array which we return in the end. And that's the merge sort algorithm. Now let's analyze the time complexity. For the merge sort and for its time complexity, it's very simple. For the best, average, and worst case, we always have the same time complexity. We don't care about the order, we don't care about the input at all. This algorithm always performs exactly equal. We always have a time complexity of O of n times logarithm of n. And that's a pretty good time complexity and certainly better than quadratic time complexity. Now, how can we derive this time complexity? Of course, with that good old master theorem function here, or with this approach. Because we're dealing with recursion, and we have a recursion where we split the problem, the input data, into smaller chunks. So, as we did it before, we first of all will derive the runtime of the recursion, of the recursive step, and then thereafter, the runtime of the code outside of the recursion, And then we'll have a look at these three cases and see which case is the right one for us here, and then derive the runtime. So let's start with the runtime of the recursive step. So recursive step runtime, or time complexity, I should say. Time complexity. This, of course, is O of n at the power of log b of a. And here we have two nested recursive function calls. We call sort twice. So a would be 2, because a is the number of recursive calls, basically. And every time we split the problem into 2, and pretty much perfectly into 2. So b is also 2. So this is O of n at the power of log 2 of 2. And we already learned before that this is in the end O of n at the power of 1, which is just O of n. So our recursive step runtime is O of n. Now the time complexity outside of the recursion. What would be our time complexity there? Well, in the end, that's the code here at the beginning and the code after our sort function. Now, the code in the beginning, that's constant time. There is no loop in there. There is no nested function call that would matter. So that's constant time. Here, after our recursive calls, we have a loop, and that's of course always something we want to look out for. We have a loop, and you know, a loop typically means that it's linear time. Now, it could be more than that if we had a nested loop. It could be less than linear time if we split the problem into 2 here as well. But no, this is a fairly simple loop. In the end, we just go through our arrays. Yes, we go through 2 arrays, but not in a nested loop, where we would have every step times 2, but instead this is more like going through one long array. So in the end, this is also O of n here. It's a regular loop, no nested loop, nothing like this, so this is also O of n. And back on our slide, this means we're back to this case here. We got the same work inside and outside of the recursion, and hence the overall algorithm runtime or time complexity is simply O of n at the power of log b of a times log n. Now we learned that this here is just n in the end, right? And therefore we got O of n times log n. And this is exactly what I showed you on the slide. This is the runtime of the merge sort. Now, throughout the module, you saw this merge sort algorithm, the bubble sort, and the quick sort. And you saw that these sorting algorithms have different runtimes. Now, you also saw that the merge sort algorithm pretty much beats the other sorting algorithms. So, of course, you might be inclined to always use the merge sort algorithm. And for longer arrays, that probably is right, though it is worth pointing out that the merge sort algorithm, of course, also contains a lot more code. So for shorter arrays, it might actually take longer, now measured in milliseconds and not theoretically, than maybe the bubble sort algorithm, which only looks long here because of all the console log statements. In the end, it is relatively short. So the merge sort algorithm certainly has a bit more code to it, and therefore it's more complex to write, and it might not be the best tool for every sorting task you have, because it might just be overkill. The performance advantage, the time complexity advantage it has, might not always matter. But if it does matter, if you should come up with the sorting algorithm with the best performance, now then this merge sort algorithm here certainly is a good candidate. As mentioned though, it requires more code, it's a bit more complex to write and to understand, which can be disadvantages that matter, and it also takes up quite a bit of memory because we create a bunch of intermediate arrays. We create a bunch of temporary arrays. These 2-element arrays, we split all these arrays. We got a bunch of memory occupied here with this algorithm. That might or might not matter, but that's also something worth keeping in mind. For the bubble sort, for example, that's not something we have. And that leads us to space complexity. another dimension we can use when we compare algorithms. We'll learn more about it in the next module. In this module, it's time for space complexity. Now, thus far we focused on runtime, on time complexity, on the big O notation for time complexity. That's what we used thus far in this course to compare algorithms. And I can already tell you, time complexity, so what we used thus far, typically is the far more important measure for comparing algorithms. In interviews, but also in discussions with colleagues, you will in 99% of cases talk about the time complexity. Nonetheless, we also have another dimension we can use when we want to compare or judge algorithms, and that would be the space complexity. So in this module, we'll take a closer look at what space complexity actually is, how we can derive it for our algorithms, and of course we'll dive into some examples and judge some of the algorithms we already saw in this course by their space complexity. So what is space complexity then? It's actually not that hard. Time complexity allows us to judge how long an algorithm will take, and more importantly, how that runtime, that time an algorithm takes, grows with bigger input values, so with a bigger n, with longer arrays, bigger numbers, and so on. Well, space complexity is essentially the same for space in memory. We judge how much space in memory an algorithm occupies whilst it's running, and just as with the time complexity, we of course focus on the general trend there. How does the space occupation grow for bigger input values, for longer arrays, for bigger numbers? Now, of course, it's important to understand that in JavaScript, all values you're working with are stored in memory. Every number, every object, every string you store in a variable or you use in a calculation is stored in memory. It has to be there, otherwise it wouldn't exist in your program. Now, data is stored in memory all the time, therefore, but your values are also frequently released from memory if they're not used anymore in your code. And all that memory usage is managed automatically by your JavaScript engine, so by the browser, for example. Of course, especially arrays and objects can take up a bit more space in memory though. Therefore, when we judge space complexity, we typically focus on those. But I don't want you to think that only arrays and objects are stored in memory. Everything is stored in memory, but also everything, including arrays and objects, is released from memory if it's not getting used anymore. And generally, in JavaScript development, we don't need to worry about memory usage and space complexity that much. Of course, we can write inefficient algorithms. Of course, we can write code that has memory leaks or consumes a lot of memory. But generally, browsers and JavaScript engines are relatively smart about managing your memory, and therefore it's not the #1 priority we typically focus on in JavaScript development. Of course, we never want to introduce memory leaks, but that's a bug. That has nothing to do with space complexity. Space complexity really is just about the memory usage we have in an algorithm without having a bug, and therefore that's what we'll focus on in this module. So it is a dimension we can have a look at, and we will have a look at it in this module. We'll also see how we can derive it, but it's really important to understand that space complexity typically is not the #1 criteria for comparing algorithms in JavaScript. So how do we derive space complexity then? It's relatively straightforward. When we analyze our algorithm and we want to judge the space complexity, we have to find places, lines of code in our algorithm where values are stored permanently in memory. Now, with permanently, and that's why I put it between quotes, I don't mean that it's there forever. I just mean that, for example, if you have a loop or a recursive function, it survives that loop iteration or that recursive step. So if you have a loop that runs 3 times, that has 3 iterations, you would create a new value with every iteration, and the value from the last iteration would also still be used, so that you add one new value with every iteration. That's what I mean with permanently. It's not getting cleared up after a loop iteration. It really is important for the entire runtime of your algorithm. As long as your algorithm function runs, data is used. If that's the case, then I refer to such data as permanent data. Of course, it will typically be cleared up once your algorithm is done, but I'm really just talking about the data management inside of the running algorithm. So we want to look out for values that survive multiple loop iterations or multiple recursive steps in our algorithm, and then we simply count how often such permanently stored values are being created. So how many such permanently stored values we have in our algorithm. And that then allows us to determine how that number of permanently stored values depends on n, and this ultimately allows us to derive a big O notation. And yes, we also use the big O notation for space complexity, and there we also can have a linear or quadratic or exponential or logarithmic, all kinds of space complexities in theory. Because, of course, we could have an algorithm where we, for example, create a new object with every iteration in a loop, and we loop through all numbers up to n, and we keep the created objects around after every iteration. Then we would have linear space complexity because we would create more and more objects and keep those objects around with a growing n. Of course, we'll see some real examples in just a second, but that's how you can derive space complexity. So, time for some examples. And for that, we'll have a look at a couple of algorithms, their space complexity, and a short reason why we have that space complexity. And I want to start with an algorithm we saw relatively early in the course, and that's the factorial algorithm, and here the loop-based variant. So that algorithm that gives us the factorial of a number. Let's see which space complexity this algorithm has. Here's this algorithm, the factorial algorithm, where we have a loop to derive the factorial of a number. And now the question is, which space complexity do we have here? Now for that, I mentioned on the slide that we first of all have to find places where permanent data is stored, and that we then should count those occurrences and see how this depends on n. And when I talk about values being stored, I don't just mean objects or arrays, I also mean numbers or strings. So what's going on in this algorithm? When it starts, we create a new variable and we store the number 1 in it. So that's one value that's getting stored in memory. Actually, even before that, the number parameter we're getting, that acts as a variable we can use inside of the fact function, and that's therefore also getting stored in memory. So once this line 4 finished executing, we already have 2 values stored in memory, number and result. Now we create a loop, and in the loop we loop through all numbers up to number, almost starting at 0 or 1, though we start at 2 for the reasons mentioned earlier in the course, but roughly we go through all numbers up to n. We have that I variable, which is created here, and which gets a new value with every iteration. We have that boolean here, which is created and checked with every iteration. And we update result with every iteration. So how many new values are getting stored with every iteration? Well, we store a new I, and we create a new boolean here. But also important, after every iteration, that boolean and that I we used for that iteration is not needed anymore. It's cleaned up, it's not referenced anymore. Instead, when the next iteration starts, a new I and a new boolean is created, but the old ones from the previous iteration are no longer needed. So therefore, that's not permanent data because that does not stick around after every iteration. The I is recreated with every iteration, but the old I's from the previous iterations are not used anymore. So therefore, we actually create no new permanent data here. And then we return the result. So if we have a look at this algorithm, we don't create that many values that would be getting stored in memory, and we actually have no data at all that would be stored in memory and that would grow with a bigger n. Because even in that loop, we just recreate values, but we are not interested in the old values. So we only have one new value around all the time, essentially. And therefore, the space complexity of this algorithm is actually constant, O of 1. That means that the space in memory we occupy does not depend on n. It does not depend on the number. If we feed in a number of 10 here, we use the same amount of memory as if we would feed in a bigger number. Now, of course, if we had to measure it in bytes, there might be small differences because of bigger numbers or anything like that. But the general trend is constant because we don't suddenly occupy twice or 3 times as much memory as before. So that's how we can judge the space complexity of this algorithm, and that is the space complexity of this algorithm. I hope it's relatively straightforward how that worked. And with that, we can, of course, fill out this first row in this table here. We know that the factorial algorithm, if we use a loop-based solution, has a space complexity of O of 1, so a constant space complexity. And that's the case because we operate at one and the same number throughout the entire algorithm, and we don't create any new pseudo-permanent values throughout this algorithm. Now let's compare that to the recursive version. Maybe think about this on your own first. In the next lecture, we'll derive its space complexity together. So let's explore this alternative factorial function's space complexity. The difference, of course, is that here I'm using a recursive approach. We're calling ourselves. Now, what's the space complexity here for this algorithm? Is it also constant as for the loop-based solution, or is it maybe different? Now, one word about the time complexities first. There we had the same time complexity, no matter if we used the loop-based or the recursive solution. So that did not differ, but maybe there's a difference for space complexities. And indeed there is. For the loop-based solution, we had constant time because no new permanent values were created. For the recursive solution, that's different. There, when we execute this, number is stored in memory, as for the loop-based solution. And then here we create a new 1 and a new Boolean. Those are only created temporarily and dropped immediately after they're being used, essentially. But then here we call ourselves again. And what's the impact of that? Well, as you know, for recursive functions, when you call yourself again, a new function execution is pushed on top of that execution stack. That means the first function call simply waits for the result of the second function call. So we got kind of 2 ongoing function calls now. Of course, only one function execution runs at the same time, but the first function call, is waiting for the result of that currently ongoing function call. Now, because of that first function call, when that whole function started, has its number stored in memory. But then when we call this nested function here, so when we call ourselves, we of course create a new function execution and we pass a new argument to that nested function call. So that function call on its own, of course, occupies some memory, but also the argument we're passing to it, that's a new number in memory that has to be stored. But keep in mind that the parameter we received on the first function call also still is stored in memory. So with every new function call, we create a new number in memory that has to be stored besides the previous numbers, which also still are stored because those previous function calls didn't finish yet. And therefore, for this recursive solution, we actually have a space complexity of O of n. So we have linear space complexity because with bigger n's, we create more values in memory. And there is a linear relation between that because we call ourselves n times. And that's of course pretty interesting because we had the same time complexity for the two factorial algorithms, as I mentioned a second ago, but we have different space complexities. So if we compare these two approaches, we could lean towards the loop-based solution because it has the same time complexity as the recursive approach, but it has a better space complexity. Now, of course, we're not talking about a horrible difference there. The space complexity, as I mentioned earlier, might not really make a huge difference, but it is something worth noting. Of course, maybe the fact that the code here is a bit shorter and could even be written in a yet shorter way, maybe that outweighs that disadvantage, but it is something worth noting. We have different space complexities here. So that recursive factorial algorithm has a linear space complexity because we create a new value for every nested function call. Let's explore other algorithms. Let's maybe have a look at linear search. What's the time complexity of that? For linear search, which is this algorithm we derived in the search section, what's the space complexity there? What's the space complexity of linear search? Well, let's have a look at that algorithm. It's not a recursive algorithm, instead we use a loop. We're getting a couple of inputs, a couple of arguments here, and of course they're all getting stored in memory. But no matter how long the array is we're passing in, we only create 2 or 3 values in memory here. Of course, you could say that longer arrays probably take up a bit more space in memory, but that's some browser, some JavaScript internals. The space occupied in memory doesn't necessarily grow with bigger arrays, or at least there isn't necessarily a linear relation. And even if that would be the case, that's not exclusive to our algorithm. So we don't care if a longer array takes up more space in memory. That's the case in JavaScript in general. We care about our algorithm. How does our algorithm work with the input data, and how much extra values in memory are we creating in that algorithm? So we create 2 or 3 values here, we create 1 value here, and that number of values does not depend on n, on the length of this array, at all. But then we have a loop and we go through all items in the array. So for every loop iteration, we basically create a new constant item which holds one of the array items. But just as before with I in the loop-based factorial algorithm, we only have one item in memory at the same time. Because after every iteration, we basically ignore, we drop the previous iteration's item and only focus on the new item. So therefore, no longer how long the array is, we typically have only one item around at the same time. So this is not permanent data, this is just temporary data that's being stored in memory here. So this also does not depend on n, it does not depend on the length of our input array. Well, here the if statement, we also have a couple of temporary booleans which are used in place and don't matter thereafter, the same here. Then we return, and then I increment my index, but important, it's still only one number stored in memory. Yes, we increase it by 1, but that simply means that a new number replaces the old number. So we don't add a new value in memory, we just change an existing one, so to say. And therefore, overall, this linear search algorithm has a space complexity of O of 1, so constant space complexity. Because it doesn't occupy more space, it doesn't create more values in memory, I should say, for longer arrays. The space, the number of values in memory does not depend on n at all. So we got constant space complexity here because no new permanent values are created during the iteration. Now, what about binary search? How does this look like? For that, let's have a look at the binary search algorithm. And like earlier, try deriving this on your own first. Pause the video, derive it on your own first, and then after a quick pause, which I give you to pause this video, we'll derive the space complexity of binary search together. So, were you able to figure out the space complexity here? Let's again do it together. We got two input values, so that's two places in memory. And as mentioned earlier, we don't care about the length of the array. Yes, it might take up more space in bytes, but that's nothing our algorithm can influence, and the relation also isn't necessarily linear. Then we create two more new values, but again, the number of values we created thus far, 4 values after all, does not depend on the length of the array. We always create 4 values up to this point. Then we have a while loop with a temporary boolean, which is created anew with every iteration, and previous booleans are dropped, are not needed. We create a new middle index, but we do this inside of the while loop. So with every loop iteration, we create a new middle index, but we drop the older middle indexes. We don't create any new indexes that we would keep around. This is recreated with every loop iteration, and we don't refer back to the previous ones, so therefore they can be cleaned up by JavaScript. So this again is just one value in total that's being created. The same here for this temporary boolean, this temporary boolean, and here we update the values in start index or end index, but as explained with the linear search, where we also incremented index, this does just change an existing value. It does not create a new value that's kept around side by side with the previous value. And therefore, the space complexity here of the binary search is also O of 1. It's a constant space complexity because at no point do we create new permanent values. So for binary search, we have a constant space complexity for the exact same reasons as with the linear search. Let's now maybe have a look at some sorting algorithms, and let's start with the bubble sort algorithm. What's the space complexity of that? Again, feel free to derive it on your own first, we'll do it together thereafter. So here's the bubble sort algorithm, and let's again have a look at it. We get our array, we create our result array, which is our copied array. So 2 new values in memory. Now we have nested loops. We create this variable and this variable inside of a loop. And with every new iteration, we create a new variable. And the old variable is dropped and ignored. So same reasoning as before. This is not data that would be kept around. This is simply data that is temporarily created. Of course, outer L is kept around for every iteration in inner L, but we still have only one outer L. We don't create multiple outer L's per inner iteration or anything like that. So then we have this, we have our loops, we create inner L, as I said, will be replaced with every iteration, so only one inner L in total is kept around. We have a temporary boolean, which is only, which is replaced with every iteration. We replace values in our existing array, but we don't add any new values to that array. We just replace existing values. We swap values in the array. So we don't create new values that would exist next to the old values. Instead, we just swap values. And therefore, you might already be guessing it, here we have a space complexity of O of 1 again. Again, constant space complexity, as for many algorithms here, as you can tell, because we don't create any new permanent values. So same reasoning as before here for the bubble sort. Now, it will get more interesting for the quick sort though. So let's have a look at our quick sort algorithm. What's its space complexity? Again, we get the array, we create the copied array, so that's 2 values stored in memory, and the number of values here doesn't grow with a bigger n, with a longer array. We have this if check, which has no impact on space complexity. And then we have something interesting though, which is different from the other algorithms, or most other algorithms we had a look at before. Here we create brand new arrays. Now that's still only two values in memory which we create here. So at this point, we are still talking about constant space complexity. The same if we count in these elements here. But now something interesting happens. Instead of the while loop, we now get a new current element. This is getting replaced with every iteration. But then we push this element either into the center, the smaller, or the bigger elements array. So into one of these arrays up there. And now that means that we have a new element that is being derived here, which we push into our existing arrays. So now we're having a new element which survives a loop iteration. After every loop iteration, that element is not getting dropped or anything like that. Instead, it increases our smaller, bigger, or center elements array. So those arrays grow with every iteration. And we have new current elements created with every iteration, which are kept around in those growing arrays. However, of course, you can argue that since we shift the element we're going to store from the existing array, overall, our space consumption doesn't really grow. Yes, we have a brand new element, which we also keep around after every iteration. But on the other hand, we shrink another existing array by that value. So we essentially really just move that value from the copied array into one of our other arrays. So here we have an interesting effect, but overall, memory consumption and the number of values in memory doesn't really change here. So it's kind of a false alert here in this array. If we wouldn't shift it, if we just would extract it, and then of course this algorithm wouldn't work, but if it were a different algorithm, if we wouldn't remove the element we're storing in a new array, but we just copied it into a new array, then we would have an impact on space complexity. But here we don't have it, and we actually still have constant space complexity. But we're not done at this point. We then call ourselves here recursively. We call ourselves twice. And by doing so, we of course have our nested function calls where we create new values in memory. And therefore here we have the same scenario as with the factorial function, with the factorial recursive version I mean. We have a space complexity of O of n, simply because we create new values in memory and the number of items we create in memory grows in a linear way. The bigger our n, the more items we're going to create in memory, and it grows at the same rate. Now, you actually might wonder why it's linear space complexity though. After all, we call ourselves twice, right? In lines 130 and 131, we call quicksort. So you could argue that every time we call ourselves twice, so we should actually have quadratic space complexity here, not linear space complexity. But for that, it is important to understand that with recursive code execution in JavaScript in general, line 130 will execute first, and it will dig into that, you could call it, branch of recursive sub-function calls first. So only when that function call in 130 and all other function calls that are triggered from inside that function call finished, only then it will move on to line 131. So you can always imagine such a recursive function call as a tree of nested function calls, and we saw such a tree of function calls earlier already when I talked about exponential time complexity. And if you imagine that, it is important to understand that only one branch of that tree executes. So therefore, we'll first go through all function calls that resolve from line 130, and only once that is done, we'll go through all function calls that resolve from line 131. And therefore, we'll never have more than n extra values be created in space. So that's why we have a linear space complexity here and not quadratic space complexity for the quicksort algorithm. Though I will say, theoretically, you could achieve O logarithm of n. This is possible with a slightly different version of the algorithm, which you also find below this video as an example. So because of these nested function calls with new values that are being created, we have O of n, or with a little optimization in a different approach, O log of n. So here we have a different space complexity. And you can already see the pattern that recursion typically gives you not constant space complexity, but instead linear space complexity often. Now let's have a look at one last example, and that's merge sort. Again, have a look at it on your own first. We'll derive it together in the next lecture. So here's the merge sort algorithm we worked on. Now in this algorithm, we are doing a bunch of things, and up to this point we have no impact on space complexity. But then here we do something which is a great trigger for us. We call ourselves. We call ourselves with shorter arrays, but together they give us one long array, basically our original array, and we do this recursively. And therefore we create a bunch of new arrays in memory, and the number of arrays and the values stored in these arrays, so the size in memory occupied by those values in those arrays, that simply depends on n. The longer the array we pass in here, the more we'll split up our arrays here, and the more new arrays with new values are getting created. And we have a linear relation here. The while loop doesn't really make a difference there. We don't call ourselves recursively or anything like that, and we're only working with temporary values. But because of that recursion, we have a space complexity of O of n here for our merge sort algorithm. And that completes our table here. So overall, space complexity actually isn't too tricky, and very often you will have either constant or linear space complexity. You typically have linear space complexity if you call yourselves recursively. And of course, theoretically, you can have other space complexities like quadratic space complexity and so on as well. Maybe if you have recursive calls inside of a loop, but that is not that often the case. And as I mentioned in the beginning of this module, space complexity in general is typically not the most important dimension which you can use to compare algorithms, but instead it's just an additional dimension which you should be aware of and about which you now learned how you can derive it and how you should think about it.